This is video 3 for the circuit unit. So one of the things we need to talk about is how to get an electrical shock. And the damaging effects of an electrical shock really comes down to how much current is passing through the body. Now, current does depend on voltage. We learned that, V equals I, R. So a greater voltage means a greater current. And but it also depends on the resistance. So if I have high voltage and high resistance, the current may be very small. But if I have high voltage and low resistance, the current can be very high. So again, the current depends on the voltage that's applied and the electrical resistance of the human body. So skin, the resistance of skin. If you have your hand soaking in salt water, the resistance of your skin's around 1,000 ohms. And if your skin is nice and dry, then the resistance will be around 500,000 ohms. So on average, we can assume right around 100,000 ohms. So what that kind of means is that we usually do not feel 12 volts, and maybe 24 volts would just barely start to tingle. So here's some numbers, and this is all current. So 0.001, that's 1 milliamp. You can feel that. Five milliamps is painful. Ten milliamps will cause your muscles to involuntarily contract, and that can be dangerous because it can send your heart into fibrillation. 15 milliamps, you can have a loss of muscle control. And then 70 milliamps, if that can go through your heart, it's probably fatal if the shock lasts longer than 1 second. So 70 milliamps, that's not a lot, but that can be very, very dangerous. So many people are killed each year from the current from a common 120 volt circuit. So basically what's coming out of your wall outlet. If you touch a faulty 120 or 110 volt light fixture in your home with your feet or your hands on the wire and your feet on the ground, there is an 120 volt electrical pressure between your hand and the ground. So the resistance to electrical current is the greatest between your feet and the ground, so most people would not be seriously hurt, especially if you're wearing special rubber boots. But if there's water around your feet, let's say you're in a bathroom and there's some water on the floor, that resistance quickly goes away. Another thing, as electricity starts to pass through your body, your skin's resistance breaks down and becomes less resistive. So it's kind of a cascading or a chain reaction like effect. So once you start getting a shock, it can become very damaging very quickly. So to receive a shock, there must be a difference in voltage between one part of your body and another. Electrical current will follow the path of least resistance between those two voltages. The ground is always considered to be 0 volts. Now this is why birds can sit on high voltage power lines with both of their feet on the same voltage. So if I were to take a look at this bird right here, this foot might have a voltage of 500,000 volts. But this foot also has a voltage, 500,000 volts. There's no potential difference. There's no difference in voltage. So when the electricity comes along this wire, or the electrical current, I should say, it's going to pass straight through, because if it were to try to go up into this bird, the bird is a resistor, and there's just less resistance to go through the wire than it is to go through the bird. However, If this bird were to somehow touch two wires, now there is a voltage difference, especially if the current is going one way through one wire and a different way through the other one. There will be a very large difference in voltage. Now we can start talking about some circuits. The first type of circuit is one that's called series or in series. And basically, what I mean by series is that we have two loads that are in line. So electricity will flow out of the battery and then return to the battery. We can illustrate this with lamps or resistors or anything like that. Conservation of electrical charge tells us that all of the charge that leaves the battery must return to the battery. So if I have 20 amps coming out of the battery, I must have 20 amps return to the battery. And that's due to the law of conservation of electrical charge. Because remember, current is charge with respect to time. It's counting how many charges pass a point in the wire per second. So in a simple series circuit, the same current will exist almost immediately in all parts of the circuit when the switch is closed. The current does not pile up in any lamp or resistor, but it flows through each lamp and resistor. So looking through this one, if I have 3 resistors in this circuit, all 3 resistors, you'll notice, receive the same current. Any break in that path will result in an open circuit and the flow of electrons will stop. Since the current is constant through this type of circuit, the voltage that's impressed across a series is divided up among the individual electrical devices in the circuit, so that the sum of all the voltage drops across the resistance of each individual resistor is equal to the total voltage supplied by the source. And this just comes from the fact that the amount of energy given to the total current is equal to the sum of the energies from each device. So going back to this example up here, remember Ohm's law says that V equals I times R. So I can calculate the voltage for this resistor. I can calculate the voltage for this resistor and that third resistor. And using that, notice that I is the same for all 3 of them, but all 3 of them have a different value for R. What I would find is that for this circuit, 9 volts would equal that V1 plus V2 plus V3. If you want to, you can pause the video, pull out a calculator, and multiply those up real quick. Just be careful with the kilo ohms and the milliamps. So here's another example. We have 4 voltmeters. Might be hard to read this, but this one says positive 45 volts. This one says negative 10 volts, negative 20 volts, negative 15 volts. And notice that 15, 20, and 10 add up to give me 45. Now, you may be wondering about the positive or negative part of it. Really what it is the voltage of the power source plus all the individual voltages have to add up to be 0. So that's why we assign those one, like the ones inside the circuit, to be negative and the power supply to be positive. It's really not that big of a deal. So the voltage drop across each device then is proportional to its resistance, and this follows from the fact that more energy is dissipated when the current passes through a larger resistor than when the same current passes through a small resistor. So here is another quick example. We can see all the currents, 120.78 milliamps I got two resistors, and we got the different voltage drops. And notice that the smaller the resistor, the smaller the voltage drop. The larger the resistor, the larger the voltage drop. So big resistors will drop the voltage by a greater amount than smaller resistors. So it can be easy, hopefully, to see the main disadvantage of this type of circuit. If even just one device fails, the entire circuit's done. Cheap Christmas lights work like this, where you plug in a strand of lights and none of them work. You have to go through each single light to find the burnout bulb. That can be a real pain. So one way to get around this is to use parallel circuits. So in this one, notice that the current comes out of the battery and then gets split into two currents at this junction, which we call a node or a junction. So take a look at the difference here between series and parallel. So electrical devices connected to the same 2 points of an electrical circuit are said to be connected in parallel. The total current in a parallel circuit is divided among the parallel branches. Since the voltage across each branch is the same, the amount of current in each branch is inversely proportional to the resistance of the branch. So here's what I mean by that. If this power supply is 9 volts, the voltage across each resistor or light bulb or whatever will be the same, 9 volts. That might be kind of hard to visualize. Basically, what's happening is the current is divided up. I1 and I2 are both smaller than the main current I. So that allows the voltage to be the same. So the total current in the circuit then is going to be equal to the sum of the currents in its parallel branches. Now, I'm not going to make you guys do math with this, but I do want you to understand that if you want to buy high quality Christmas lights, you want to make sure that the bulbs are wired parallel and not in series. Okay, the next thing I want to talk about is equivalent resistance. So what that means is I can take any circuit and take all the resistors in that circuit and represent them as one resistor. That one resistor would be the equivalent resistance, or it's like the resistance of the entire circuit. For series, the equivalent resistance equals the sum of all the individual resistors. So for this example right here, the equivalent resistance would equal 20 plus 19 plus 20, which is 59 ohms. So if I could find a 59 ohm resistor, it would be the same as that circuit. Parallel is a little more tricky. The equivalent resistance for a parallel is the sum of 1 over all of the individual resistances. and then we have to inverse that. So for this one, the equivalent resistance be 1 over 10,000 plus 1 over 2,000 plus 1 over 1,000. And then I have to invert that. And that gives me 0.625 kilo ohms, or 625 ohms. Notice that the purpose of resistors in series is to increase the resistance of the circuit, and for parallel to decrease. The equivalent resistance of a parallel is smaller than your smallest resistor. 625 is less than 1,000. Now, resistors can get quite complex. We're not going to look at all of these, but there are circuits out there that have elements of both parallel and series. And a fun class activity I'll probably do would be to give you a circuit and have you boil it down to its equivalent resistance. But I'll show you how to do more of that in class. The math is pretty easy, and it's nothing really to worry about too much. All right, we'll conclude this unit on circuits.